That is, Amanda, what my plan was. So, and I am trying to adjust the wrong screen. So today the plan is an introduction to chirality, and then talking about constitutional isomers, diastereomers, enantiomers, and stereoisomers. Just going over that, and then differentiating that from conformers. And there's a lot of words there, and they all end in "er." So, what is chirality? So this won a Nobel Prize 2 days ago, which is pretty good. And it was actually organocatalysis that won a Nobel Prize 2 days ago. But the media spent all of its time talking about chirality. And we had a drinking game in chemistry Twitter to take a shot every time you read an article where somebody talked about your hands being chiral. There were a lot of very drunk people on Tuesday because that seems to be the best example. And so it's of course, it's the freaking example I am going to use. Essentially, chirality is a function of three-dimensional space. If you have any object in 3 dimensions, like a tetrahedron, for example, or my hand, which, you know, there's 4 bits on a tetrahedron. My hand kind of has 4 bits. You can go, okay, so, and you can look at your hands too and really look at your hands. You got a little finger, you got a thumb, you got a palm, you got a back of your hand. So you got 4 bits, you got 4 things. Anytime you have 4 things arranged in 3-dimensional space, there are 2 ways you can arrange them. It's just the way it is. A physicist probably has something to say about this. I am not a physicist. Mathematicians. Seems like a set theory thing. So here's one way to arrange those 4 things. Middle, little finger, thumb, palm, back of hand. My other hand is the other way to arrange those same 4 things. Little finger, thumb, palm, back of the hand. Why is it a different way to do it? Well, I can never actually superimpose them. I can't make them into the same thing. They are 2 different things. If I try and arrange middle finger and thumb, then my palms are not pointing in the same direction. They're pointing at each other, not in the same direction. If I try to arrange my palms so they're pointing in the same direction and the back of hand, then my thumb and little finger aren't. Anytime you have 4 things arranged in 3-dimensional space, you have chirality. And you can actually have it in fewer than 4 things. In the lectures, I talked about this. I talked about screws. Screws have chirality. Otherwise, you get really confused. That's why you get really confused if you have like a left-handed screw or right-handed screw, whichever one's not the normal screw, and you try and turn it to tighten it and it's loosening. You're like, what the hell's going on? It's because you expect it to be chiral. You expect it to go one way. That is not a very technical definition. So a technical definition for chirality is something is chiral if it has non-superimposable mirror image. Okay. So what does that mean? Well, you got a mirror image. Look at a mirror. Can you then rotate that mirror image? Not take the mirror image of the mirror image, because that's the first thing, but can you rotate that mirror image to be the same thing as the first thing? So just rotating. I'm going to see if I can stop sharing and see if I can expand my screen. Okay, I'm spotlighted, but that didn't actually help doing anything. So spotlighting doesn't help. I think you might need to gallery full screen. Maybe full screen? Nope, that doesn't help. I have no idea if you see a big picture of me, and I just don't see a big picture of me. Okay, good. I'm going to get my balls. I keep a big box of balls in my filing cabinet, so you never know when you're going to need them. If I had anything else more entertaining to say, I'd say it, but I actually need to pay a little bit of attention to what I'm doing here. Otherwise, I'm going to make two of the same thing, and it's going to be a pain in the ass. Okay. So, I got myself the same molecule. So I have a molecule here. It's a carbon. It's got 4 things attached to it. Notice I can rotate it any way I want, and I'm not changing them all. It's the same molecule, right? I'm rotating it. So there's all sorts of different ways I can draw this tetrahedron. It's the same tetrahedron. I'm not breaking any bonds. I'm just moving it around. That's fine. Another molecule. Now I want you to pretend that there's a mirror between my 2 molecules. And sorry, I'm going to point it that way. So I'm holding on to this. My hands are too fucking big. Trying to hold on to the middle carbon. Ooh, I'm going to stick. I know what I'm going to do to make this easier. I'm going to stick some big ass carbons on it, and then I can hold on to the carbon like a handle. Never thought of doing this before. Okay, there we go. So if you're looking at these are mirror images of each other, right? You can pretend there's a mirror down the middle. The red is at the top and close to the mirror. The green is at the bottom and close to the mirror. The white is kind of in the middle and close to the mirror, and the black carbon bond is pointing directly behind. But these are mirror images of each other. Now, what I can try and do is I can try and superimpose them on each other. So if I put the reds together and the blacks together, then the whites and the greens do not superimpose. These are chiral molecules. So they have 4 different things. Now, I go fishing in my box of balls, and I pull out some green balls. Again, these are mirror images of one another. I've got the reds up and close to the mirror, the greens down and close to the mirror, and the 2 other greens out, and then the blacks pointing back towards me. These are mirror images. Now, however, they are superimposable mirror images. They were mirror images. There's no question about that. They are also superimposable. I'm able to put everything on top of the same thing. Now, those of you who are paying attention notice I cheated. How did I cheat? Well, this green ball is the mirror image of that green ball, but that's not who I superimposed it on. I superimposed it on the other green ball. It's just I can't tell one green ball from another. So they are mirror images, but they are superimposable mirror images because I'm able to put everything on top. Why does this work? There are not 4 different things attached to this carbon. The carbon has green balls, red ball, black ball. And I'm able to superimpose the green balls on each other because I'm kind of cheating by superimposing the wrong green ball on itself. So there's a sort of a general rule here that generalizes from green balls to other things. Shit. I deleted it because I didn't like my nomenclature. Is never a source of chirality. So a tetrahedral carbon is never a source of chirality if it is attached to two of the same things. Okay, I'm being very careful there. A carbon is never chiral. This is something I think I mentioned in the recorded lectures as well. Textbooks kind of suck at this. Molecules are chiral. Objects are chiral. A carbon is a source of chirality, or a stereocenter. People use the term chiral center. It's incorrect, but it's fine. You can use chiral center. I don't care. It is technically incorrect. So chirality is a function of an entire object, not of a single carbon. A carbon inducing chirality in the entire object makes it a stereocenter. So a tetrahedral carbon is never a source of chirality, or is never a stereocenter, if it is attached to two of the same things. So in that case, we had our carbon attached to two green balls. It was not going to be a stereocenter. Okay, so that is basically chirality. There's no secret third way. There is two ways to make a molecule. So what I want to talk about briefly is the difference between chirality, diastereomers, enantiomers, and constitutional isomers. So there are all sorts of different types of isomers. By source of chirality, I mean that makes the molecule chiral. So a molecule is chiral because one of its carbons is attached to four different things. One or more of its carbons is attached to four different things. The carbon itself isn't chiral, but the carbon being attached to four different things is the reason the molecule is chiral. So we can call that carbon a source of the chirality, or the reason the molecule is chiral. Or we just call it a stereocenter. Does that make any sense, Melitza? Okay, we're going to do examples and we'll see if it makes any more sense. Okay, let's say we have this molecule and we have this molecule. Are those isomers of each other? Well, first of all, are they the same molecule? It's always a good question to ask. Are A and B the same molecule? The turkey's kicking in early. Thanks, Selwyn. And Madison. And Hannah. And Faith. Sorry, I was trying to give the question mark in the sound there. They're not. They're not the same molecule because stuff isn't attached to stuff in the same way, right? Like, you can't name these and come up with the same name because carbon 2 is attached to two methyl groups. Carbon 2, either way, is not attached to two methyl groups. They're not the same molecule. Okay, so they're not the same molecule. Not same molecule. Good question to always ask yourself. Okay, so then same connectivity. Well, yeah. So what does this mean? This means, are all the atoms attached to the same atoms? If I look at carbon 2, is it attached to the same atoms in both cases? It's a flowchart. Everyone likes flowcharts. So connectivity means is everything attached to the same things. Hold on, Selwyn, I'm relying on you here. Okay, Olivia's with a no, Alyssa's with a yes. Okay, we have disagreement here. Let's be careful what we mean by the same thing. So what we need to make sure is let's count carbons. And it's not just the same type of atom is attached to the same things. But in this case, carbon 2 is attached to 2 methyl groups. And here, carbon 2 is not. And it doesn't matter if I count carbon 2 from the other side. They do not have the same connectivity. Because if they did, both carbon 2s would be attached to the same thing. The answer is no in this case. This means these are constitutional isomers. Because they are constituted differently. And I think isomers is one of those terms you come across in high school organic chemistry. And isomers are 2 molecules. Molecules are isomers of each other if they have the same molecular formula. So I guess the first question is, do they have same molecular formula? Always worth checking. Obviously, if they do, sorry, yes, they do. Sorry, that's a yes, not a no. Because if they don't have the same molecular formula, they're not isomers. They're just completely different molecules. A pen is not a Pepsi bottle. Like, they're just not. I don't need to think too much more about that. And, you know, these 2 molecules I made earlier, well, we argue that these were the same molecule. So I'm going to put my white balls back on. Oh, shoot. So these 2 molecules, the ones I'm holding in my hand, bring them up real close to the screen. Do these have the same connectivity? Yeah, we'll talk about that in a second, Melitza. So first question is, do these have the same molecular weight? They have all the same things on them, so yeah, same molecular formula. It's hard to tell if they're the same molecule, so you can kind of skip that question. Do they have the same connectivity? Yep, they do. They do. You can tell they're not the same molecule because they're not superimposable. I try to superimpose them and you can't, so they're not the same molecule. They have the same connectivity. This carbon is attached to a blue ball, a green ball, a red ball, a white ball, and a black thingy. This one's attached to a green ball, red ball, white ball, and a black thingy. They both have the same connectivity, but they are not the same molecule. Okay, this is where we get the next question. This is where it gets tricky. We've already assigned that these are not the same molecule. Okay, there's two ways to phrase this question. The first way is going to be more useful down the line. The second way is more direct. So what's the question asking? Are all the stereocenters mirror images of one another, or are the molecules mirror images of one another? These are the same question. I'm just phrasing it slightly differently. We'll talk about why the first one is a useful way to do it in a bit, but let's talk about the second one because it's a little bit clearer. We've already decided these are not the same molecule. We could not superimpose them. We tried way up there at the top. But now we know that, yes, these are mirror images of one another. That makes them enantiomers. Compounds that are mirror images of one another are enantiomers. There are always pairs of enantiomers. You never have a single one. They always come in pairs because one is they are mirror images of one another. The working definition of enantiomers, I go over in the lecture, so I'm not going to write it down here, is that enantiomers are non-superimposable mirror images. They are these are mirror images of one another, and they are non-superimposable. When I try to superimpose them, I can't. That makes them enantiomers. So what's this no thing? So let's say we have the same connectivity. Yep, okay. So I'm going to do another example of this. And for that, I'm going to need more balls. And then I'm going to start sharing my screen, stop sharing my screen so you get to see more of me. You lucky people.
Yeah, I'll be back when I'm done school, bro.
Somebody is unmuted. Mohammed. Just heads up. It's all cool, but it's nice to know you're committed. Okay, I'm gonna just quit sharing for a moment. So am I back on the big screen now? Because we're gonna look at these guys. You know, the chat takes a little longer to update than my Teams. Okay, cool, awesome. Okay. So I'm gonna mess this up by rotating something. Okay, so let's say we have these two molecules. Each of these has two stereocenters. Let's just look at one for a second. What do I mean by a stereocenter or a source of chirality? Let's call it a stereocenter. This carbon here, what I'm pointing at, is attached to four different things: white ball, red ball, green ball, black stick. This carbon center here is attached to four things: blue ball, white ball, green ball, black stick. This is attached to four things, that's attached to four things. Both of these are potential stereocenters. We have the same thing with the other guy, and we note that they have the same connectivity, right? One carbon is attached to red ball, green ball, white ball, black stick. The other carbon is attached to white ball, green ball, blue ball, black stick. So every atom is attached to all the other same atoms. They have the same connectivity. We can check first to see if they're the same molecule. I can't superimpose the blue ball side of this. So there can't be the same molecule. Okay. Now, the question is, if you go back to your flowchart and if you've written it down, are these molecules mirror images of one another? I don't know. I just made them, but I can't actually remember what my answer to that question was. So what I'm going to do is I'm going to make the blue ball side of this, and we agree that the top, this blue ball side, are mirror images of one another. But if I just rotate the molecule without rotating any bonds, the bottom one's not. So it's really tempting to say, aha, it's not a mirror image. Remember, you can rotate bonds. So let's try and rotate bonds. Oh, it is a mirror image. I just rotated the carbon-carbon bond. You can always rotate single bonds. Now these are mirror images of one another. I really hope they are. Yes. So the top and the bottom are both mirror images of one another. We can just doubly confirm it. They are non-superimposable mirror images of one another. You know, I can't trying to put the blue on blue and the green on green, and the other stuff doesn't superimpose. It's all screwed. So these are mirror images of one another. They are non-superimposable mirror images of one another. They are enantiomers. Okay, I have made a new molecule. Haven't touched the blue carbon, blue ball carbon. Still mirror image. Red ball carbon. Can't tell. It's not clearly not. Well, no, I can. I've lined up the red ones here. That is not a mirror image, right? The white is where the green is. The green is where that's not a mirror image at all. And if I try and rotate it, shit, that's not a mirror image. But if I try and superimpose that bottom carbon, holy shit, it superimposes. So wait a second. Okay, top carbon mirror image. Bottom carbon, not a mirror image. Are these molecules mirror images of one another? I'm looking at Fatima as the last person to answer that. My big face was here. Right. So we're getting no's, which is great. If any part of it's not, if any of the atoms is not a mirror image of its representative on the other molecule, the whole thing can't be a mirror image, right? Like it can't, because that's just not how geometry and optics and stuff like that work. So we have things that are not mirror images of one another. I think I have graduate students trying to get into my office. Tricky little things. So, well, what the hell is this? Because same connectivity. Yep. Are all the stereocenters mirror images of one another? Nope. These are diastereomers. Diastereomers are things where you have the same connectivity. They are not the same molecule. But they're not mirror images. I want to sort of phrase this a slightly different way. I'm sure I did this in the lectures, but it bears repeating.
Dr. Trant, we can't see what you're writing if you are writing anything down.
Yeah, that would be a good idea. Thank you. Sorry. Wow, thank you. yell at me when that happens. So the no is a diastereomer. The other thing I've noted here is we called the no up here, if they have different connectivity, we said they're constitutional isomers. Constitutional because they're constituted differently, not because they believe in life, liberty, and the pursuit of happiness. And then if they are showing the same connectivity and they're not the same molecule, because we already checked that, then they're called stereoisomers. And that's because they differ in the three-dimensional arrangement of items. So, you have a stereo system, you got a left and a right speaker. Don't mix up your left and right speaker. Your speakers are, they're mirror images of each other, but if you mix your left and right speaker, you get a different listening experience. And it's confusing. Because then you hear it differently in headphones and at home, and it's all just weird. So stereoisomers are things where stuff is different. Are isomers where stuff is differentially arranged in space around the carbons. So if the compounds are mirror images, they're enantiomers. If the compounds are not mirror images, they're diastereomers. So diastereomers are two stereoisomers because you're always comparing one to one. These things always happen in pairs. There could be many versions of a diaster. There could be many different diastereomers present, but you're always looking at this one versus that one. Two stereoisomers where some, greater than one, but less than n stereocenters have so where n equals the total number of stereocenters. So we've got, this is what this is. So we've got two stereocenters on this molecule, greater than or equal to 1. 1 has flipped, but not 2. Because if 2 had flipped, no, less than. If it's equal to, then you're fine. If 2 had flipped, then we'd have they both would have flipped. They would be mirror images of each other. By flipping, these are the same. These bottom ones are the same. By flipping, I switch two groups. I make it the mirror image. And so if I switch to, I make it the mirror image. It's not the same stereocenter. So these two, this stereocenter, this red ball stereocenter is flipped. It's not the same thing. They are mirror images of each other. So now these whole things are mirror images of each other. I've now gone back to the enantiomer. Apparently I can't hold a pen and two molecules in my hands at the same time. You ever wish you were an octopus? So you have these so right now these are enantiomers. Both stereocenters are mirror images of each other. The whole molecule is a mirror image of each other. 0, like of these, how many stereocenters have flipped? 2 of them. There are 2 stereocenters. All 2 have flipped. They are enantiomers. So enantiomers are cases where every stereocenter is the mirror image of every other stereocenter. Every one is flipped. Diastereomers where at least 1 is flipped, because if 0 flip, it's the same molecule. But if 1 or more flipped, but not all of them, then you have diastereomers. That's the difference between enantiomers and diastereomers. Let's do some examples. Okay. So again, if you have a lot of trouble with this, I'm going to show you some ways to cheat because it's, you know, it's legit cheating. So here are two tetrahedra. Just one carbon. These cannot be diastereomers of each other. So first of all, are they? We have to kind of invert that last flow chart because we don't know if they're the same molecule yet. If you can tell it's the same molecule, great, you've actually solved the problem. But we can sort of say, yep, the carbon is attached to four things, and the four things are the same in both of them. We also know they cannot be diastereomers because there's only one chiral center. And if you only have one stereocenter, see, I still say it. If you only have one stereocenter, I was badly trained. Like my dog. He doesn't say chiral center, but he woofs at everything. So if you only have one stereocenter, it is not possible to flip one or more stereocenters, but not all of them. Because if you flip one or more, you are flipping all of them. So if you have one stereocenter, you do not have diastereomers. You only have enantiomers. You only get diastereomers if you have more than one stereocenter. What do I mean by flipped? I mean they are mirror images of each other. So, sorry, this is my terminology. I consider these two flip, this blue ball one, these to be flipped stereocenters. They're flipped from each other because they are mirror images of one another and are non-superimposable. Whereas if I swap two of these groups, this is actually a fundamental property. If you swap any two groups on a stereocenter, you flip it to the other one. So if I swap two of these groups like I just did, suddenly they are superimposable. They're the same stereocenter, the same carbon. So flipped means they are non-superimposable. So you swapped things. I use the term flipped. There is no actual term for this. The proper term is they are enantiomers of each other. Or the stereocenters. I'm trying to avoid using naming right now because I want to talk about that next class. And I think we can get really caught up in naming. Naming matters, of course, but identifying this stuff is, I think, more fundamental because name is just a freaking label, and a stereocenter by any other name is just as irritating. So let's look at these. And what we need to do is we need to determine, are these the same molecule or are they different? There are 3 ways you can do this. There are 4 ways you can do this. There are a lot more than 4 ways you can do this. So one way you can do this is build a model. Initially, build a model. I'm going to show you how to do it on paper. Build a model initially, because you're going to want to try and get this 3-dimensional thing going. It's important. And so you could build a model, rotate it, and see if it works. Great. The second thing you can do is you can rotate this in your mind. How do I do that? Well, the easiest way is, if you're given a question like this, is to identify one of the atoms that doesn't move. If I'm looking at all these, the chlorine is in the same place on both of those. It's both in the sort of the out coming towards me position. Let's say I have a tetrahedron like this. And you have the chlorine, which is maybe this green ball coming out towards you. You can spin. It's going to be hard because it's sticky. But I can spin the other 3 atoms around to their different positions without breaking any bonds, without changing this from one thing to another. I'm just rotating. So can I just rotate along that carbon-chlorine bond to get them to the same place? So what I'm going to do is I'm going to use what I call my rotation arrow. This is not a formal arrow. You won't find this in any textbook. We really need it. but it doesn't exist. I'm just saying I'm rotating. I'm not doing any chemistry. No chemistry is happening. No resonance is happening. No equilibria are happening. I'm just rotating a freaking bond. So draw my tetrahedron. Chlorine hasn't moved. And what I want to do probably is I want to try and get this, I want to be able to compare the two. So in my mind, the fastest way to do this is rotate this, if I'm rotating around this bond and I'm rotating this way, the methyl group moves from this position to up to this position. The fluorine moves to that position. The bromine moves to that position. To who here does that make sense? Like you can see, I go, oh yeah, that makes sense. I like how that rotates. I'm curious. I really actually want to hold a poll on this one day because I know for some of you this is great. For some of you are going like, I do not fucking understand what just happened, and that's okay. Okay, so some of you get it. Anyone just go like, I do not understand what just happened. Oh shit, you're a miracle group. Okay, Emily, good. Got it. Do me using the kit. Okay, Amanda, you're in the I don't fucking know what happened. Which is cool. That's okay. Because this does not work for everyone. Kind of. Okay, well, we got some kind ofs. We got a little bit of confusion. This is great. If you are confused by that, please get out a model kit, make that and do that twist for yourself. You can do that later. You will get it. You might still not be able to see it great on paper. So one thing we can do is we can try and rotate a model kit. We can rotate this in our minds using the power of our minds. Or we can do the cheating way. The cheating way works. You just need to count if you're good at counting. I am not particularly good at counting. So for what I'm going to do is I'm going to redraw A. Call this A and B. It's very convenient that A and, well, B I guess is boron, but C is carbon. Yeah, the alphabet's stupid. I wish we, anyways. I'm going to redraw A. I'm going somewhere with this. I promise. Okay. What I'm going to do, and I'm going to show you why this works. So I'm just not blowing smoke. Though I need to get all the right balls on the right things. Let's get my stick back. Sorry. That's for, so Hannah, that's for naming. And so we're going to talk about that in a second. Yeah, Amanda, I got you. If you have a hard time visualizing 3D, you are at a disadvantage to all these naturals in here. I do too. I've been doing it a long time, so I'm better at it, but I am not a natural at it. You're at a disadvantage to all these people who are naturals at doing it. Use your model kit if you have a hard time seeing this in 3D. Is it always counterclockwise, says Alyssa? Nope, you go in there, I can rotate clockwise, I can rotate counterclockwise, I can rotate clockwise, I can rotate whatever the hell this is. Like, you can rotate however you like. It just needs to be a rotation. Can you explain it one more time? Yes. We'll do another example of that in the next example. Okay, what I want you, this is like a magician's trick. I want you to convince yourself, looking at these cards, I mean molecules, that these are mirror images of each other. You know, pick your card, put it back on the deck. Okay, these are mirror images of each other. I'm going to take my molecule here, and through a sleight of hand, which really isn't very good because I'm a shitty magician, my wife told me that for her birthday under COVID, she wants me to do some magic tricks. I have about a month to learn some magic tricks, and my hand-eye coordination is okay, but my speed isn't. And by magic tricks, of course, it's like, you know, card stuff. I have you saw me switch two atoms. I literally ripped an atom off, and I ripped the other atom off, and I swapped their positions. And I was talking about my wife and magic tricks and trying to misdirect you. I wasn't trying to misdirect you. I might have, though. So if you didn't catch the magic trick, I ripped off the green, I ripped off the white, and I switched their places. Now when I do that, remember they were mirror images of each other. They are now superimposable. They are now the same molecule. They are no longer mirror images of each other. Right? This is just a truism of tetrahedral centers and tetrahedral atoms. If you switch any two groups, if I physically rip off the blue, rip off the green, stick the green where the blue was, stick the blue where the green was, not rotate anything, I have made, you can rotate, it doesn't matter, but I didn't have to. You have made the enantiomer. That is how this works. It's just, I know I'm frustrating because I always say it depends. It's a case-by-case situation. You have to balance these different things. There's no balance here. These are enantiomers. This works every single time. So how can I make use of that for our evil plan? Well, what we need to do is we need to make sure we draw A and B. Yeah, if you have one stereoisomer for read, it is either a mirror or a superimposed. If it's superimposed, it's the same molecule. If it's a mirror, they're enantiomers. If you have more than one stereocenter, it can be diastereomers, in which case it is neither a mirror nor superimposable. And that's why we go back to that flow chart. So I've drawn these in the same way, and by that I mean, hey, the V of the stuff in the bond is the same way. We have an out to the right and a back to the left. It's, you know what, if we erased all the substituents, you'd see the stick figure would be the same and would be superimposable. What I'm going to do is I'm going to switch two groups, and I'm going to try and make A look like B. Well, I didn't understand that. My phone agrees with the class. So the fluorine wants to go to this position here. So I'm going to switch the fluorine and bromine. I'm just physically ripping them off and switching them. I'm not touching anything else. I'm not rotating anything else. I'm not thinking about anything else. I've just switched those. Okay, so I've got the fluorine where I want it in B. But now I don't have the bromine where I want it. I want the bromine here. But luckily, I want to switch the bromine in a methyl group. And if I do that, I'll get B. So notice I am not rotating here. I am physically going in there with my little molecular scissors, and I am snipping off a atom, and I'm snipping off another atom, and I am gluing them back on in a different place. Like, this is just how I wish chemistry could be done. I'll be really slow doing it atom by atom, but still, principle. This is equal to B. Okay, cool. You randomly switch some things with like just breaking rules and not doing chemistry. This is not chemistry. This is not possible to physically do. How does that help me? Now what you do is you count the switches. 2 switches. Okay, so if you remember, one switch, one flip, one switch, same thing, I guess, gives you the enantiomer. 2 switches gives you the enantiomer of the enantiomer. And just like, you know, the enemy of my friend, or the friend of my enemy, or whatever. The enemy of my enemy is my friend. You got 2 enemies. That guy's my enemy. His enemy is that guy. So we're both ganging up on this guy and we're taking his lunch money. 2 switches. You make me the enantiomer. You make the enantiomer, you're back to me again. So 2 switches equals same molecule. Superimposable. Because if you are a superimposable molecule, you are the same thing because you are superimposable, which means you are the same thing. Because if you're not the same thing, you're not superimposable. 1 switch would have been the enantiomer. So what we can say here is even number of switches equals same molecule. Odd number equals enantiomer. This always works. This is just a truism. It's 220. Do you guys want to? I know some of you have the fun of going to lab. Yeah, I knew that would come up. Okay, so let's do this. These 2 carbons are enantiomers, right? Non-superimposable mirror images. I made 1 switch to 1. Now they're superimposable. So they were enantiomers, and now by switching 2 of the groups on the enantiomer, I made the enantiomer of the enantiomer. And the enantiomer of the enantiomer is the original thing. Now if I make the enantiomer of the enantiomer of the enantiomer, so I make another switch, this gets ridiculous pretty fast. I'm back to being enantiomers. Because there's only 2 states. You're either the same molecule or you're the mirror image of the molecule. You're the enantiomer of the molecule. Those are your 2 options. If we're talking about 1 chiral center, 1 stereocenter. So you switch back and forth between being the mirror image and not being the mirror image, like being the same molecule. And then the mirror image, then not the mirror image. The mirror image, and not the mirror image. You don't go anywhere. You just flip back and forth between these 2 states, like 0 or 1, 0 or 1. There are no 2s. So if you make an even number of switches, like 2 switches, first switch makes the enantiomer, the second switch takes you back to the original molecule. Make 1 switch, takes you to the enantiomer. If you make 3 switches, so an odd number of switches, the first switch makes the enantiomer, the second one takes you back to the original molecule, the third one takes you back to the enantiomer. And you can scale these as far as you want. You can do 999 switches if you like, and that's going to be the enantiomer because it's odd. That's really stupid. Please don't do that. That's a real waste of your time. Unless like you're a real fidgeter and you just like, switching, and when you count at the end of the day, you've done 999 times. I fidget a lot. Main reason I like chemistry because I always had model kits in class and I could just, wiggle them. Do you guys want another example, or should we bring it up next class and screw it? Let's enjoy the long weekend. I'm having turkey and pork. Oh, Madison, I like that. Yeah, I guess it is. Probably, yeah, just, yeah. Okay, let's do another example. Okay. Make this one a little bit harder. Okay. So far we've been talking about simple balls. This one's a little bit different in that, is that middle carbon attached to 4 different things? I don't know what the question, the answer to that was they were the same molecule, Melissa. We were able to find out the same molecule either by rotating or by doing the switches or by building models. These two, are these the same molecule or not, is the question. So I guess my first question is, are these carbons attached to 4 different things? Perfect, Olivia. Yeah, it's attached to the same thing. Attached to two of the same things or 4 different things? We have, I think, Madison. Like these are not constitutional isomers. They're all attached to the same. They're the same thing. But any given molecule, are those 4 different substituents on it, or are 2 of them the same? I think we're getting they are attached to 4 different things as the consistent answer, and that's right. 2 of them are carbon, but they're not the same carbon. One's a methyl group, one's an ethyl group. Methyl groups are not ethyl groups. They are different things. So both carbons are attached to 4 different things. Now, if we're going to try and do the rotation thing here, as I said, the first thing was look for a bond that doesn't change between them. Bugger. I messed with you, and all the things are in different positions. So, well, we can take care of that by rotating. So let's rotate around. For those of you who are rotators, there's no right way to do this. Any rotation is valid. They are all equally valid. It doesn't matter if I rotate like this, like around this blue. I'm holding a blue ball in my hand, or I rotate like this, or I rotate around the white one. It's all the same. None of this matters. It's all identical. You're not changing the molecule. All those are valid ways of doing it. But let's spin around the top. And let's spin the other way. So let's get the fluorine where we want it. You can get any of them. It doesn't matter. There's no right way to do this. This is the way that jumped to me first. So if the fluorine moves there, the iodine moves to where the fluorine was, the methyl moves to where the iodine was. Right? Because if I'm spinning around like this, everything moves one step. In my view, it is clockwise. Yeah, so clockwise. Whee! Everything moves one step clockwise if one of them moves. They stay clockwise relative to each other. Or counterclockwise. You could have gone counterclockwise. That would have been fine too. So now I have the fluorine where I want it, but nothing else is. So now I'm going to rotate around this carbon-fluorine bond. You never need to do more than 2 for this. You can if you like, but you can always do it in 2. And so when I do that, let's say I rotate. Never a bad idea, just drawing a tetrahedron first. I put the methyl group, the ethyl group down here, so I'm rotating the ethyl group. So the iodine rotated up to where the ethyl group was, and the methyl group rotated to where the iodine was. So this is a rotation thing. So we can see from this that these are the same molecules. And then Olivia just jumped in and did the whole switcheroo thingy. So, and let's take Olivia's advice and swap the F for the methyl. Count, one swap. I am Z count and I love to count. So by doing that one swap, I have made the enantiomer. It is still not the product. And then she wants to switch the iodine for the ethyl, which is perfectly valid. And we do that. And oh, look, we've made our product. Again, just like with the rotations, you never need to do more than 2 switches. You can, and sometimes I sometimes do anyways because I just don't see it. But now we know that this is the same as that. 1 switch, 2 switch, this and this are the same molecule. Or so this and this are the same molecule because this is that. So you can get there either by rotating or by doing the switching thing. Both are completely valid. Both will work every single time if you don't screw them up. If you screw them up, they don't work. Sure. I was just asked, can I do an odd switch example? I will. So I'm going to start with the same starting material. Sorry, the same guy on the left. And how do I know this is going to be an odd switch? Because I just made the enantiomer. That's how. Okay, so how do I turn these guys into that? Well, I'm going to switch. Nope, John, don't use a resonance arrow. Bad, John. F switches for methyl. So I have the methyl in the right spot. Now, if I want to get the iodine in the right spot, I'm going to switch the iodine for the fluorine. Again, I'm just switching, trying to get one atom in the right place. I could have done this in 2. But there's no reason to. That involves too much thinking. And I am running on about 2.5 hours of sleep, which will probably be your experience during the exam. And so don't try and get the perfect switch, just do it. Okay, iodine and methyl are in the right place now. Now I need to switch the fluorine and the ethyl group, and I do that. I really want to draw resonance structures or resonance arrows. I really shouldn't, because I get upset when people misuse resonance arrows. Kind of hurts me in my soul. Swap the fluorine for the ethyl. For some reason, I don't consider that a resonance arrow because it's not a structure. It's just like atoms. It doesn't make any sense. I agree. And now if I compare this to that, I see that they're the same thing. I count the number of switches. 1, 2, 3. 3 switches. Therefore, an enantiomer. Does it matter which one we switch into? No, you can switch any 2 things you like. Olivia, you can just go ahead and swap anything you like. It doesn't matter. Like when I was swapping groups, I could have swapped the green balls, the blue balls, the white balls, the black stick. I swapped balls because the stick I was holding on to it, so it was harder for me. But it wouldn't have mattered. This is any switch you make, any at all, gets you the enantiomer. If you're not convinced, go home, build. If you probably are home, build yourself 2 models, enantiomers of each other, and just start randomly switching things. And it doesn't matter what you switch. If you start with enantiomers, you switch any 2 groups, you get the other one. Okay, I'm going to leave it there for today. I hope it was a helpful addendum to the course delivery. There are questions on this on the assignments. Yeah, you could have switched from the right molecule to the left. That would have been fine. You can actually switch both of them and meet in the middle and then count the total number of switches involved. All that is fine. It all takes the same thing. I don't recommend switching both of them. I would just pick one. But it doesn't matter which one you pick. Okay, happy Thanksgiving, everybody. Enjoy your vacation. Or 3 days of bliss and then reading week, whatever you're going to be doing. I muted myself as I turned my camera off. Have a really good reading week. I'm stopping recording.